Hi, this is Grishma MS studying in Sri Venkateswara College of Engineering. Today, we can see applied physics for CSE stream. Topic is de Broglie hypothesis. Let's start the video. Introduction to de Broglie hypothesis. The de Broglie hypothesis is a fundamental concept in quantum mechanics proposed by Louis de Broglie in 1924. It states that the particles such as electrons and photons can exhibit wave-like properties. The hypothesis is based on the concept of wave-particle duality, which suggests the particles can be behave both the particles and waves. De Broglie hypothesis, we have seen that radiation has dual behavior waves like the particle like. In 1925, de Broglie suggested that the same is true for matter. V is equal to E divided by H as we can see in the image. Specialized, he proposed that the frequency and wavelength can be associated with the electrons, energy and momentum. Here lambda is the de Broglie wavelength. So there is an equation E is equal to PC is equal to HC is equal to HC divided by lambda. Lambda is equal to HP. The de Broglie relation hold for photon. Next, the de Broglie hypothesis suggests that not only does light exhibit properties of both waves and particles, but particles such as electrons and other subatomic particles can also behave as both waves and particles. In other words, particles possess wave-like properties and their behavior can be described by the wave associated with the particles of momentum. De Broglie proposed that the wavelength associated with particle is inversely proportional to its momentum. This relationship is expressed as lambda is equal to h divided by p, where lambda is a wavelength, h is a Planck's constant, and p is the momentum of the particle. This equation shows that particles with higher momentum have shortest wavelength, while particles with lower momentum have longer wavelength. The de Broglie hypothesis has experimentally confirmed shortly after its proposal, and it was a crucial step in the development of quantum mechanism, leading in the understanding the particles and the wave are two aspects of the same underlying reality. At the quantum level, it has the since become the principle of quantum mechanisms and plays a significant role in the principle of quantum mechanism and plays behavior like particles in the microscopic world. Wave-particle duality. According to wave-particle duality, particles can exhibit both particles-like wave-like properties. Particle-like behavior refer to the particles of distant position and momentum. Wave-like behavior refer to the ability of the particle to exhibit interface and diffraction patterns similar to the waves, as we can see in the image. De Broglie wavelength. The de Broglie wavelength, represented by lambda, is the measure of the wave-like nature of a particle. It is calculated using the equation lambda is equal to h divided by p, where lambda is the wavelength, h is the Planck's constant, and p is the momentum of the particle. The de Broglie wavelength is inversely proportional to the momentum of the particle. The situation is different for low energy electrons and other microscopic particles. Consider a particle with kinetic energy k, its momentum is found from. So k is equal to p squared divided by 2m. Its wavelength in the lambda is equal to h divided by p is equal to h divided by root 2m k. Let's see the derivation of de Broglie hypothesis, which is based on the wave-particle duality concept. There are stepwise. Let's see the first step. Wave-particle duality. The wave-particle duality is the idea that particles can exhibit both wave-like particle-like behavior. This concept was first introduced by Louis de Broglie for for any particle, we can associate a wavelength with its which characterize its wave-like nature. Step 2. Relation between momentum and wavelength. De Broglie proposed that the wavelength of a particle is related to its momentum. He derived this relationship based on the following assumption. The first assumption was a particle of momentum is related to velocity v and the mass m as follows: p is equal to mv. The waves associated with a particle has the phase velocity and the equal to the particles of velocity. Step 3. Let's derive the equation. We start by considering the de Broglie wavelength of the particle. The Broglie wavelength is given by lambda is equal to h divided by p, where lambda is the de Broglie wavelength and particle, and h is the Planck's constant, as we seen in the last. And we can take the approximate quantum mechanics like 6.626 into 10 to the power minus 34. For assumption 1, we can express momentum p as p is equal to mv. Now we need to relate the velocity to the phase velocity of the associated wave. According to the assumption 2, these velocities are the same. Wave is equal to v. Step 4, expressing the wavelength and the terms velocity, and the next we want to express the wavelength in the terms of the velocity of the particle. We can do this by combining previous equations. Lambda is equal to h divided by p. Since p is equal to mv, lambda is equal to h divided by mv. Step 5, simplification. Now let's further simplify the expression divided by both numerator and denominator by the mass. Lambda is equal to h divided by mv is equal to h divided by m into v. So the step 6, de Broglie wavelength equation. Finally, we have derived the Broglie wavelength equation if a particle is lambda is equal to h divided by m into v. This equation represents the de Broglie hypothesis, which states that any particle with the associated wavelength given by the above expression. The de Broglie wavelength is a concept of quantum mechanics and plays a role of describing behavior and particle level. Next, experimental evidence. So we have seen the de Broglie derivation. So we have to prove that this is existable. So the de Broglie we have an evidence to prove this. The de Broglie hypothesis was experimentally confirmed by the Dimension in German in 1927. They observed the differentiation of electrons when they secreted on the crystal lattice, similar to the differentiation of X-rays. This experimental provided a strong evidence for the wave-like nature and particle and supported to be de Broglie hypothesis. This was the evidence for de Broglie hypothesis. And experimental verification of de Broglie hypothesis was taken in USA, where studying in the scattering electrons in the nickel crystal in a diagram of their apparatus. And we can see the diagram in the image. Application of de Broglie hypothesis. What are the application of de Broglie hypothesis? Laid foundation for the development of quantum mechanics. It used to explain phenomena such as electrons differentiation and behavior particle in accelerators. The concept of wave-particle duality and the de Broglie wavelength are the fundamental understanding behavior particle in the quantum level. Let's see the significance in modern physics. The de Broglie hypothesis or understanding of behavior particles, it paved the way of development and quantum mechanics, which is essential to understanding the behavior of matter, energy, and atomic and subatomic levels. The hypothesis has advanced our understanding of fundamental nature and particles in the wave-particle duality. So, what are the contribution and recognition? Louis de Broglie was awarded the Nobel Prize in Physics in 1929. His discovery of the wave nature of electrons, his hypothesis has had profound impact of the field of physics and continues to shape our understanding of the quantum world. The de Broglie wavelength is an essential concept modern physics in the widely used various branches of science. Last, conclusion. The de Broglie hypothesis proposed that the particles can exhibit wave-like properties leading in the concept of wave-particle duality. It is supported by experimental evidence and has our understanding of behavior of particle. The de Broglie hypothesis contains a fundamental concept and modern physics. I hope so this video is helpful to you guys. Please like, share and subscribe. Thank you.